Hey everyone, and welcome to this explainer. Look, if you've ever stared at a math problem just completely packed with letters and numbers and felt that sudden awful knot of anxiety in your stomach, I want you to take a deep breath. Seriously, you are in exactly the right place. Today, I'm going to be your personal tutor, and we are going to translate the physical world into simple, understandable math, together, step by step. You see, math isn't just a bunch of random rules trapped in some dusty textbook. It's actually the secret language behind calculating a shopping discount, measuring land for a house, figuring out building design, and even compressing the data on your phone. So let's dive right in and see how this language actually works in the real world.
To start us off, we're going to tackle a real-life scenario, specifically measuring land. Imagine the sports committee of Denora High School wants to build a new coco court. But, they don't just need the court itself. They want to leave a space of equal width all the way around the court for spectators to sit. The big question is, what exactly should the width of that space be? Now, if you're staring at this problem on a board exam, it might feel pretty overwhelming. Like, where do you even begin, right? Well, my absolute favorite trick is to just break all that noise down into two simple buckets: what is given and what is asked.
Before we even look at any scary formulas or letters, let's just list out the concrete numbers we know for sure. We're given the total area of the rectangular plot they have to work with, which is 558 square meters. We are also given the exact dimensions of the inner playing court, 29 meters long by 16 meters wide. And that's it. That is our solid foundation. So what is asked? The width of the spectator space. Whenever we don't know a value in math, we just give it a temporary nickname. Let's call this unknown equal with x. Now, here's where it gets really interesting: how we take those numbers and make them real. The golden rule here: always draw the shape before you even touch a formula. Let's look at this diagram together. Right in the center, you can see the inner coco court with its poles. We know it's 29 meters long and 16 meters wide. Surrounding it is this pink border. That's our spectator space. We've labeled the width of that space x meters. And because the committee wants an equal space all around, that border is x meters thick on the top, the bottom, the left, and the right. Honestly, seeing this visually is the absolute key to unlocking the whole shebang. Okay, now that we have our visual, let's literally build the total length of the entire plot of land. We start with the inner court's length, which is 29 meters. But the plot extends beyond that, right? We have to add the spectator border on the left side, which is x meters. And we have to add the spectator border on the right side, which is also x meters. So the total length is 29 plus x, which neatly simplifies to 29 plus 2x. Now, I want to pause here for a second, because this is absolutely crucial. In a rush, a student will often just write 29 plus x. They completely forget that a border surrounds the court on both sides of the length. That's a super common exam trap. But by checking your drawing, you can see clear as day why it has to be 2x. Moving on, we use the exact same logic to build the breadth or width of the plot. We start with the known inner breadth, 16 meters. We add the border on the top, which is x meters. We add the border on the bottom, which is, you guessed it, x meters. So our total breadth becomes 16 plus 2x. Notice how patient we're being here? We haven't even really done any complex math yet. We're just describing a physical rectangle with some very simple expressions. So, the magic moment is connecting what we just built to that big number they gave us at the very beginning. The total plot area is 558 square meters. Now, how do we find the area of a rectangle? You probably learned this years ago. It's just length multiplied by breadth. So we magically translate our physical diagram into algebra by taking our total length expression, which is 29 plus 2x, and multiplying it by our total breadth expression, 16 plus 2x, and we set that whole thing equal to 558. And just like that, boom, you have successfully set up the math problem. The hard part is literally over. Now we just gotta tidy things up a bit. We multiply those two groups together. 29 times 16 gives us 464. Then we do the cross multiplication, getting 58x and 32x, which adds up to 90x. And finally, 2x times 2x gives us 4x squared. So our equation looks like this first line here: 4x squared plus 90x plus 464 equals 558. To solve equations like this, we want to bring all our numbers to one side so the other side is exactly 0. We subtract 558 from both sides, giving us 4x squared plus 90x minus 94 equals 0. And finally, check it out. All those numbers are even, right? So we can divide everything by 2 to make our lives way easier, leaving us with our final simplified equation: 2x squared plus 45x minus 47 equals 0. Now, if that final equation looks a little intimidating, let's put it into perspective. In your previous classes, you spent a lot of time mastering linear equations. Those are equations like ax plus b equals c. They're just simple, straight lines. Finding x was pretty straightforward. Well, this new equation we just built is just one tiny step up in logic from that. Instead of just a plain old x, we now have an x squared. That little exponent of 2 tells us we're dealing with a whole new shape. Not a straight line anymore, but a curve. And this brilliantly illustrates the definition of what mathematicians call a quadratic equation. A quadratic equation is simply an equation where the highest power of the unknown variable is a square, just like that x squared we found. And think about what you just did. You started with a real-world playground, drew a picture, followed basic logic, and built a quadratic equation all by yourself. Solving that equation is what gives you the exact width of the spectator space. You are already doing advanced math, and it's really just common sense applied step by step.
Example 2, the metal sheet box problem.
All right, imagine you're working in a workshop and you need to construct a container. Let's look at Ronnie's project. I want you to really visually picture this in your mind as I read the givens. Ronnie has a square metal sheet. That's our starting shape. She takes some scissors and removes smaller squares measuring 9 centimeters on each side from each of the 4 corners of this big sheet. After cutting those corners out, she folds up the remaining sides to form an open box. We are told the final capacity, or the volume, of this newly folded box is 144 cubic centimeters.
So, the big question asked is, can we find out the original dimensions of Ronnie's flat metal sheet? Well, absolutely we can. If we call the whole original side x, the base of our newly folded box becomes x minus 18. Why? Because we subtracted a 9 centimeter corner from both sides. The height of the box is simply that 9 centimeter fold. So using volume, which is length times width times height, we get x minus 18 times x minus 18 times 9 equals 144. You divide by 9, expand the squares, and once again, physical folding turns directly into a quadratic equation. See how that works? Section 2, the math setup cheat sheet. We've covered a lot of ground today, haven't we? To wrap up, I want to give you a quick tool you can take right into any exam to eliminate math anxiety once and for all. Here are 5 foolproof steps to setting up any quadratic word problem. First, separate the noise. Clearly identify your givens and exactly what is asked. Second, and this is your surprise trick for exams, always draw the physical shape and visually label both sides. Actually drawing it out literally saves you from the most common deduction of forgetting to add or subtract a border twice. Third, write out simple expressions for your length and width using your drawing. Fourth, multiply those expressions using a known formula, like area equals length times width, and set it equal to your given total. And fifth, expand the math and move all the numbers to one side to equal 0. If you follow these 5 steps, I promise, the problem practically solves itself. You see, math isn't just numbers on a whiteboard meant to frustrate you. It's a highly logical, highly predictable language that describes the actual dimensions of the entire world. From the borders of your local sports court to the very boxes your online shopping arrives in, it all boils down to these simple steps. So now that you know the secret of visualizing the problem before solving it, what other hidden equations do you think are holding together the spaces and objects around you right now? Keep looking at the world with curiosity, trust the logic, and I'll catch you in the next explainer.